So, let us say what they have done here is they have fixed the baseline value, which is nothing but your x1, x2, x3, x4, that is what is being done here. Okay. And then I pick a particular x and then I perturb it. By how much should I perturb it? It is between -10 and +10. So, the total range is only 20, but I also should decide how many grids I have. There I had 3 levels or 4 levels, here I would have decided how many levels I have. So, that eta divided by p minus 1. In this particular case, if I had 6 levels, then that eta should be the same for all of these guys. But then I should divide it by the number of grids, because this particular variable has 1, 2, 3, 4, yeah, okay, 5, okay, for each of thing we will make it 6. So, if the eta was 6 for me in that particular case, then it will be 6 divided by 6 minus 1 or 5 divided by 6 minus 1, okay, if I make this guy to be 5. And then you take this particular guy 0.5 to 1, okay. There also your eta should be the same, but then my p could vary, it can have only 1, 2, 3, 4, 5, okay. So, then it will be 5 divided by p minus 1 depending on which p you are looking at, okay. Anyway, if you try to do this, what will happen is I kind of get this kind of a plot. Of course, you will have to run your simulations for each of those cases, for each of the delta that you do, for the small perturbation, you find out what your value is, and this is the graph that I get. Imagine that you do not have this. This is replaced by a Farner-Ullman simulation or some complex plus CFD plus some cost model, something, okay. So, what happens is, if I go and change the weight of the fuel in the wing from 252 to 246, I will have to plug this guy into this setup, I have to run this, I have to run this, I have to run this, then it will give me a response. So, I keep these responses, and now what I am going to do is this, I am going to plot this. When I am estimating that, I am not only estimating the wing, but also meaning not only the weight, but I will also estimate the other stuff, because there could be an interactive effect. So, if I go and change the weight of the fuel in the wing, of course, the wing area, the aspect ratio might not change, but the dynamic pressure at the cruise might change, okay. Ultimate load factor might change, okay. The flight design gross weight obviously changes, okay. So, there could be an interactive effect. So, I need to go and estimate each one of these guys as well. So, when I did that, I am able to plot this graph, it is just called a tile plot. What it says is, the way that you look at this is your SW is your wing area, weight of the fuel in the wing, and then aspect ratio, quarter chord sweep, aspect ratio, quarter chord sweep, dynamic pressure, and then it keeps going like this. The same ones are listed on the other side also, the y axis also. Of course, SW will be just 1. So, I am just taking off the off diagonal terms. So, I am starting with in the reverse fashion I am doing WF, A, okay, Q, it goes in this direction. So, what this one says, this particular graph if you take, SW is fixed at its nominal value and I am perturbing WP, okay. I perturbed WP different values and I am taking a contour of SW, okay. I am just looking at this guy, okay. So, with respect to W, the fuel weight, okay, while this guy is at its nominal value, if I am changing WP, what is the effect that I am getting? You can also look it up the other way around, okay. I am fixing this WF and I am changing WDG, what is the effect that I am getting? I am fixing this lambda, okay, and then I am fixing the lambda at the baseline value, and then I am checking what my WP is by varying it, okay. Similarly, WDG, NZ, TC. So, now what this one says, the legend is the same for all of them. This one is pretty much here, this particular graph. It does not say anything. SW is what? Your wing area, sorry, and what is this guy? WP is the paint weight. The paint weight obviously will not have an effect on your wing area. So, that is what is captured here. Whereas, let us look at this particular stuff, because that is where the red is large, right. So, that is between A and NZ. What is A? The aspect ratio. What is NZ? The ultimate load factor. Okay. So, depending on the shape, the aspect ratio also tells you what is going to be the shape, or at least the size, if not the shape. Okay. That affects your load factor. Okay. And what it says is, if you go right on your A, okay, on your aspect ratio, if you keep increasing that guy, what is happening is you are also increasing your NZ. Okay. So, you do not want to keep increasing that. Okay. That is one way. The other thing is, if you look at it, this NZ is with SW, which is nothing but your wing area, and you can see that the wing area is also related to your aspect ratio. Okay. So, the point is, these kind of graphs can give you some idea. Okay. So, let us say that, see, this SW was also related to my aspect ratio. Okay. There was a relationship, and this one is WDG and NZ. WDG is flight design gross weight, has an effect on the ultimate load factor, obviously, because these aircrafts are structure fluid interaction, right. So, it will have a direct or an indirect effect on the weight per se. Okay. So, you can get a basic idea, and then you can say that, okay, these are the interactions that I am interested in, or this guy does not have an effect, direct effect. So, if this was not important, I will get rid of this. For instance, this Q does not seem to play a major role. I do not know what was Q. Dynamic pressure at cruise, maybe only at the stall speed and all that it plays a role. In this case, it does not play a role. So, you can kind of leave out those variables, or you can create sub variables. Okay. So, now we will look at how those sub variables are obtained. So, this Morris, what he said that I want to have the mean and the standard deviations, right. So, from this particular plot, I am just plotting here, but I can also get my mean and standard deviation from these plots. If I do that, if I am plotting the mean, sample mean versus the sample standard deviations, this is how the variables are getting distributed. So, what it says is, this is the origin, and around the origin there is a bunch of people who are sitting there. Okay. So, but then obviously this Q seems to be the most, okay, he does not kind of play a role, okay, because there is no variability, there is no mean value, which is what we saw in the figure also, right. Q, I arbitrarily told Q, okay, but then it turns out that that is. So, is the case, there is little bit of variability of the order of 10 for this guy, and whereas the mean is much lesser than that. Similarly, there is no variability for this FW, but he is at least mean wise. So, he has an effect, FW has an effect by itself, it might not play a role in interaction. FW. Okay. So, FW, if you can see, mostly it is straight lines, it is just linearly increasing. If you see here, other than this particular graph, all of them are linear in sense for this particular guy. If I change this, how much is it varying? Same. If I change this, how much it is varying? Same. If I change this, how much it is varying? It is varying by an order of 10 or 20, that is all it is varying. Okay. Meaning, like, if I fix this guy, if you look it up from the other sense, if I do SW, then this is what is for FW. Okay. So, you can keep doing that. And this graph gives you the same amount of information, and then but it also tells you these important guys, NZ, ASW, NZ is your ultimate load, SW was your wing area, but what it says is this guy has by himself he is important, and in interactions also he is important. NG was a dynamic cruise or what? Ultimate load factor, sorry. SW is your area. So, the area in one sense is also the same story, 40 and thing. Both mean as well as standard deviation is important. Okay. These guys have negative means. So, maybe the correlations are negative in the sense. Okay. If it is increasing, they will decrease. It is like that. Okay. TC and WDG. Flight design gross weight. How is a negative correlation? Okay, anyway, but the mean is in a negative sense, but it is important because the value is more, it is not around your 0 0. So, it kind of gives you an information. This is what Michel proposed in terms of the sampling. Okay, you should put it in such a way that if I get these details, it gives me information about the interactions. Okay, so from the plots, it also says that we can kind of appreciate what is happening in this particular mean versus standard deviation. Okay. The idea of that Morris method is important for the sampling stuff that we are going to discuss next. That is why I just out of the loop I discuss Morris method and then I am showing this for you. Okay. Now, then there is also people talking about how do you want to set your factor levels. Okay. If you are taking these two are your bounds minus 10 to 10, should you have just 0 in between, or do you also want to have minus 5 and plus 5, or should you have minus 2.5, minus 7.5, 2.5 and 7.5. Okay. So, the deal is if you can have low, you can have many, of course budget wise the number of experiments that you need to do is more or less accordingly. Okay. So, you need to make a wise decision. Okay. However, let us say that you have some information that says that this is a linearly varying quantity, then what would be your wise choice? How many levels would you choose? Good enough, because it is only linearly varying. For a line, linearly varying line or a surface, I just need 2 or 3 points. If it is a surface, 3 points is good enough. Okay, because it can vary linearly on both sides if it is a surface, that is all you need to know. However, someone came and told you this aerofoil thickness to chord ratio is not linear, but it kind of has a quadratic. A quadratic can be anywhere. I am just drawing some quadratic here. How many points do you think you need in one dimension? Okay. In 2 dimensions and n dimensions, you need to use a Pascal triangle equivalent to understand how many coefficients you need to find. Okay. So, that is what this particular thing talks about. Okay. So, you have issues with too low, you have issues with too much also. So, you want to choose, but there is no way, I mean like you will have to use these kind of engineering experiences and all that to decide upon your factor levels, that is all. Okay. So, these are some generic strategies that the co-author of these slides have given, okay, which he feels is very important. Okay. So, you have to be very clear about what is the inference space. You cannot just take raw data and then say that okay, I am going to do this. Okay. Is this really required? If this is what it is, what does that output mean? For that output, data wise this input is required, but physically does it make sense? That is what the inference space is. Use 2-level designs at the early stage, higher level designs at a later stage. So, 2-level designs kind of give you the basic idea. So, what it means is it is okay to assume linear relationship to begin with, but you will obviously identify the non-linearities over a period of time. Okay, okay, this is all the management language. So, yeah, subsequent experiments will describe the complex relationships, that is one thing. Yes, so this is a interesting point because your budget is usually given upfront. They say I give you about 1 lakh rupees. Now, decide your experiments. Let us say that your experiments are going to cost you 10,000 rupees each. You do not upfront design 10 experiments, okay, because you want to reserve multiple levels of experiments. So, you would spend about 30,000 to begin with, then another 30,000, then your 40,000. So, roughly you budget about 25% of your total budget for the initial level of sampling, that is your initial design. Okay, that is what it is. So, I guess we touched upon this, we came to this slide yesterday, is it? No? Okay. So, there are different designs. What we are going to talk about to begin with will be full factorial design and fractional factorial design, which is what is kind of an orthogonal array is a type of full factorial design, fractional factorial design. Okay. We will just quickly, we are not going to get detailed into it, and then we will talk about statistical experiments like Latin hypercube samples. So, what does a full factorial design mean? You have you remember discussing in chemistry the crystal structures, FCC, BCC. Okay, so you just remember that. Okay, body centered cube, face centered cube, that is all the idea is. Okay. So, if you take about 2 levels, what it means, there is factor 1, there is factor 2. 2 levels means factor 1 has a low and high, factor 2 has numbers 3 and 4. What I am saying is each combination I will run it. So, this guy is 1, this guy is 1, this guy is 1 and this guy is 1. So, there are 4. So, if you can draw a rectangle, all the 4 corners, this is the maximum combination I can have, you understand that, right. So, it is a full factorial design. There is a small catch to this, you think that, oh, this is so simple, why do we need to worry about it? Okay. Let us assume in this case your n, which is your dimensions, number of variables was 2 and your level, let us call it k, was 2 as well. So, this is usually given as number of experiments is usually given as k raised to n. So, let us say that you retain your level to be 2, but you increase your number of variables to 7, not even 7, 5, let us say 5 variables, this is acceptable, right. 5 is not too much. How many experiments you need to do? You make it 7, how many experiments you need to do? 128 experiments you need to do. Imagine that you are talking about what do you call that, your rotor helicopter, you know, like your helicopter failure you are trying to understand, or under a oscillatory landing condition what happens to your helicopter. Okay. Of course, you want to understand failures. So, the helicopter will fail. Can you or crash, car crash, can you crash or fail 128 helicopters? 7 factors is nothing. If you talk about a car crashing or an helicopter crashing, 7 variables is nothing. People will laugh if you say that I am taking 7 variables to evaluate it, that is very less. Okay. So, if you take 7 variables and do itself you get 128. So, full factorial experiment might be a possible way, but it is not a feasible option because you will have to keep on doing it. Okay. So, if I do, so just to give you an idea, if I do a 3 level, what does it mean in the same 2 factor, factor 1, factor 2, 3 levels means what? This is factor 2, at this particular level I have 3 levels. For this factor level, okay. Similarly, for this factor at this particular level I will have 3 realizations. So, in total 9, which is clear from this, right. So, the level is 3 raised to number of factors was 2. So, it is 9. Get the point? Okay. So, now if there were 3 factors, just to give you an idea, what will happen? Obviously, I will go to factor 1, factor 2 and factor 3. I am going perpendicular to the screen, that is the factor 3. This is how the increment happens. You see, immediately you increased it only by a factor, but the number of points increased by 4 in that particular case. It was 4 initially for just factor 1 and factor 2. When I brought factor 3, it immediately went by another 4 points. Similarly, if I had done 3 levels, in this I just did 2 levels. If I did 3 levels, then I would have got 9 points just for 2 variables, just similar to this, and if I introduce the third factor, I would have got another 9 points, which is 18. So, you understand, right. So, here imagine what will happen, 3 levels raised to 5, how much is that? 9, 9, 81, 81 times 3 is 243, 243 experiments with just 3 levels. 3 levels is nothing if you look at it. With moderate, even quadratic you saw, you need 3 points, okay, for just for 5 variables. So, it kind of exponentially builds up. So, there is a problem with full factorial experiment. You cannot do full factorial as you wish, there is a problem. And this is the way people try to do. For instance, if it is 2 raised to 3, okay, this is 2 raised to 2, this is 2 raised to 3, 3 factors and 2 levels. There are about 8 experiments, and these are all the coded factors, meaning what values which it will take, meaning coded factors means -1 is one level and 1 is another level, that is all. Okay. So, if A is -1 means it is a low level, A is 1 means it is a high level. So, so this basically tells you what are all the different combinations. See, imagine simple, you imagine this to be -1, -1, -1. That is what is this. So, like that there should be 8 points. I do not want to spend time writing the combinations, okay, but just for the sake of this thing. So, in this particular case only factor 1 changes, 1 minus so 1 minus 1 minus 1, like that for 8 points there will be the other things, and this A, B, B, C, C, A is governed by that. Let us not, these are all the interactions, these are all the interactions, okay. So, now what people said is, or rather Taguchi was the first guy to propose that, was, oh, you actually do not need to run all the experiments, okay. So, for instance, if you take 3 factors, you have single factor ABC, you have 2 factor interactions, and then you have 3 factor interactions. The assumptions and the observations are, this effect is going to be smaller than these effects, and these effects are going to be smaller this. Okay. The second thing is, you cannot estimate these without estimating this. You cannot estimate a 3 factor interaction without estimating the 2 factor interactions. So, that is the hierarchy. So, first you will have to do this, then this, then this. Okay. So, what he said is, if you are able to compromise certain things like these interactions a little bit, you do not need to run those many experiments. With only limited number of information, with only limited number of experiments, we can get as much information as we can, much more than your what do you call, like half, it is not half, meaning a half fractional factorial is not equal to half full factorial. Okay. You get much more information than a half full factorial for a fractional fractional factorial of strength half. So, full factorial, as we pointed out, is too expensive. Sometimes it is used to find the vital few. Okay. So, this is just to give you an idea, with about 15 factors and 2 levels, this is the amount of experiments that you need to do. Okay. Let me just, yeah, do not worry about the top one. These are your full factor experiments if you are talking about, okay, factor 1, factor 2, factor 3, then I need to have 8 experiments here, right. Instead, if I am looking at a fractional factorial, what it says is, you do not need to run 8, just compare these two images, you do not need to run 8 of them, you need to run only 4. So, but then the 4 should have participation from all 3 of them. So, what it says is, if you take this guy, you take this guy, you do not take the other guys, you take this guy. There are ways in which you can do this. Okay. In this particular thing, you can just say that I will take the diagonal quantity, okay, and then I will not take the projections, I will take only the diagonal quantity, but that is not how it is done. So, do not worry about that point, we will discuss how that is done. Okay. there are also ways in which you can confound, meaning confounding means you can combine. Okay. You take particular columns of the experiment and then you say it belongs to AB as well as BC. I do not know which one, but if that particular column becomes important, then I know that it is either AB, it is either AB or BC. Then I will do additional experiment to find out whether it was AB or BC, meaning interaction wise. So, we will talk about that a little bit in detail. Okay. So, now what does this fractional factorial experiment means? Okay. So, in this particular case, if you see, we are doing a 2 raised to 3, okay, 2 raised to 3, meaning 2 levels, 3 factors. The factors are A, B and C. What it says, there are 8 experiments to begin with, but you want to reduce it to 4 experiments. That is what we saw here. There were 8 experiments actually, but I told you that you just need to run only 4 experiments. So, what does that mean? How will you reduce it? Okay. Okay. There is a property of this orthogonal array. Okay. We will just go back to an array and we will discuss that. There is a property of this orthogonal array. What it says is, oh, I am sorry, this is not a orthogonal array, this is a full factorial. So, I have to go here to explain. Yeah. The column is balanced within itself. Any 2 columns are balanced between them. What is the meaning? You take any column, you can see the number of entries, right, -1 once, twice, thrice, 4 times, 1 once, twice, 3 times, 4 times. So, -1 and +1 will always be balanced. If that is 3, this also will be 3. If that is n, this will also be n. You take any 2 columns. For the sake of discussion, we will take AC and BC. You can see 1 1 happening once, 1 1 happening twice. Any other combination also will happen only twice. What is that? -1 happened once, -1 happening twice. That is it. It will not happen less or more. Okay. Okay. One sense is, I should not have used this because this is again a full factorial experiment. The actual experiment was a full factorial experiment, but the idea still remains the same. Okay. The column is balanced within and any 2 columns are balanced between them. So, you want to take this L8, L stands for the Latin square, okay, that is what this L stands for, and then the L8, 8 stands for the number of experiments. So, in this there is actually an L8. So, we are interested in going from L8 to L4. So, how will you reduce it from L8 to L4 so that these 2 properties are preserved? But you do not go about doing it, it is very simple. You can see what we are trying to do is this, we are trying to combine this C to AB. What we are saying is C wherever, meaning SCEC, where factor C and AB take the same values. Where are they taking? 1 and 1. -1 and -1. So, I am going to choose those rows and say bye. Sorry, yeah, no, I am going to only take those rows and this will just become 1. Okay. So, the only way, so if I want to run, if I want to reduce L8 to L4, okay, then I have to get rid of certain rows, otherwise I cannot do that, because 8 experiments should become 4 experiments. But which one will I use or which one will I leave out is what I need to choose, and we are using this idea to do that. Okay. So, now what happens is, in this particular case I have kind of assigned A, B, C, A, B, B, C and all that. Okay. But that is a different discussion on how to, there is something called a linear graph, there is something called a triangular table using which you allot those stuff. Okay. So, one way that you can do is combine C with AB or B with AC, you can do anything, because you remember what we spoke about, right, like A, B, C, AB, AC, BC and then ABC. So, first thing is I might want to topple this ABC. So, how can I do? I can combine C and AB, that is ABC, or I can do A and BC. So, you can look at that. For instance, -1, -1, okay, they will be the same rows, -1, -1, -1, -1. I am sorry, are you able to follow? Typically, I should have used another color, and then you can see this one again 1 and 1. It will be the same set of rows. Okay. So, the choose rows where C equal to AB or B equal to AC or A equal to BC, and then you use them, that is your half fractional. So, wherever I have those cases, I will use them. Okay. But one thing that you need to remember in this is, when you are using 2 factor, what is happening is the number of columns. If you measure these number of columns, they will be 7. For an L8 experiment, you will have 7. For an L4 experiment, how much you will have? You will have 3 columns. Okay. So, that is why I want to know which one will I combine. I will only take the first 3. Okay. So, I will say -1, -1, 1, -1, -1, -1, 1, -1, 1. Okay. Similarly, if you want to do for a 4 factor experiment, 4 factor half fractional factorial experiment, this is out of this thing, okay, like a software or something. So, A, B, C, D, A, B, A, B, C, D up to A, B, C, D. Okay. So, basically it is 2 raised to 4, which is 16. If you look at it, there will be 16 experiments in this. So, I can reduce this to L8, which is half fractional factorial, or I can, this is half fractional factorial. If I do it to 1/4, then it will be L4. Okay. So, the point is, can I do L4? Practically no, mathematically yes, because how many columns will L4 have? 3. So, it can have only ABC, but you have basic variable itself A, B, C, D, and as we have discussed, you need to have at least the first layer done. You can compromise the other things, A, B, B, C, B, D, C, D, A, C, A, D, then A, B, C, you can keep writing all the combinations. Okay. So, you can leave out these, but at least this should be preserved. So, your minimal thing, if you are talking about 4 factors, is at least L8. Okay. So, if I want to take this L16 and reduce it to L8, what I need to do? I need to kind of knock down this ABCDs to begin with. So, ABCD means I can do ABC, D separately, or ACD and B. So, if you look at it, I am taking D and ABC in this particular case. So, wherever the pink color is mentioned, it means they are taking the same value, -1, -1, 1, 1. So, I can just take only those values, and then the blue arrows tell you what are the rows that we will retain. So, we can retain, we can bring it down to L8 in that sense. Okay. Okay. So, okay. There are also other types of designs, like your central composite design. There is a face centered. Okay. So, central composite design, as the name suggests, under that there are different things. One is the face centered, rotatable CCD and all that. What is the face centered says? It says take a particular face, put a point at the center also. So, that is what we have here. Yeah. So, 1, 2, 3 and 4. So, there is a point in the center, there will be a point in the center, goes like that. Okay. So, if I build another guy, okay, then I will have, if I have another face here, I will have it like that, and then you can keep on building it. Okay. So, that is a face centered. But then what people also suggested is if you are going to put additional values. Okay. So, can I put it here? There is a problem of putting it there, because if you see from this direction, it was still only giving you 3 variables. I mean, sorry, 3 values, not variables, sorry. If you take x1, x2, what is happening is in this particular line, my x2 values are the same. For these 3 points, my x2 values are the same. So, they are not, though I am doing 3 experiments, I am getting only, with respect to x2, I am getting only 1 information value. Okay. So, is the case with anything. So, what people suggested is, instead of doing that, you can kind of do a circle. Okay. And this point will be pushed here, this point will be pushed here, this point will be pushed here, and this point will be pushed here. Okay. You might still not, you still what you call like lose information with respect to this and this particular dimension, but at least from this dimension you get additional information.
But doesn't that go out of bounds? You chose the levels as -1. What does it mean to go?
Oh, so if that is your problem, you can do it this way also. It need not be a, I mean, that is what is an inscribed circle is. Okay. So, the idea is like this actually. You can put a square outside. What I meant is, so you can just push it accordingly, whichever way you want. Okay. So, that is your inscribed circle, and also people talked about rotatable CCDs using matrix notations and all that. Okay. So, usually the Taguchi design is used in robust design principles, which is slightly out of scope, but we spoke yesterday, right. Robust design means if you have a particular response that is of interest, you want to have the variability very less. Okay, that is called robust design. You do not want a very flat variability. Okay. So, people also suggested that you need to do random experiments, you will have to replicate the experiments, and orthogonality provides you the independence of factors. Okay. So, from here what we wanted to do was this one thing, this Morris-Mitchell method and all these full factorial ideas, what they brought is this kind of a uniform sampling. Okay. Uniform sampling is one thing, uniformity is one thing. Okay. The idea is I do not have any information about this design space. So, I do not want to focus my samples at any particular slot. So, I want to explore them uniformly, that is the idea.